This is Chapter 5, Differentiation. At its core, this mathematical tool measures the exact rate at which a specific function changes. For isolated functions, the math is simple. You apply the basic power rule, drop the exponent to the front, and reduce the power by 1. But that confidence vanishes when you run into an equation like this. The power rule alone cannot resolve tangled terms. Moving forward requires a shift in focus. We have to identify the underlying architecture of the equation, spotting whether terms are multiplied, stacked, or nested within one another. To entangle these complex structures, we add 3 heavy-duty tools to the basic power rule: the product rule, the quotient rule, and the chain rule. Let's start with the product rule. Use this tool when you spot 2 different functions multiplied side by side. Notice the structure here: a blue term and an orange term sitting right next to each other. Instead of multiplying everything out, the rule dictates a specific pattern of interaction. You take the derivative of the first term and multiply it by the original second term, then add the original first term multiplied by the derivative of the second. While side-by-side terms require the product rule, stacked terms require the quotient rule. You'll use this whenever you are dividing one function by another. Take a close look at the numerator in this formula. Because of the subtraction sign, the order of operations is rigid. Swapping these terms will flip the sign of your entire result. Side-by-side terms require the product tool, and stacked terms require the quotient tool. Mapping the shape of the equation determines the path you take toward the solution. Now we arrive at the chain rule, which handles nested functions. Think of these like Russian nesting dolls, where one function is entirely trapped inside another. The first step is to apply the basic power rule to the outside function. You drop the outer exponent to the front, but keep the inside function completely untouched for now. The calculation remains incomplete until we perform the final step, multiplying that first result by the derivative of whatever is inside the box. When we break open the box and take its derivative, the full picture emerges. The chain rule is a strict sequence. Differentiate the outside, leave the inside alone, then multiply by the derivative of the inside. Let's test that sequence. Look at this fractional power equation on screen. Pause the video, identify the inside function, and apply the chain rule. First, we deal with the outside. The 1/2 drops to the front, and we subtract 1 from the exponent to get -1/2. The inside function stays exactly the same. Then we satisfy the chain. We find the derivative of the inside function, which is 5, and multiply it onto the end of our equation. Omitting that final inside derivative is why many nested function problems fail during exams. You'll often see the chain rule written in this fractional format. It represents the same concept of multiplying separate individual links together to find the final derivative. If an exam gives you a 2-part setup with a y equation and a u equation, you process them independently. We find the derivative of the y equation, and then we find the derivative of the u equation. The final step connects the links. We multiply our 2 independent derivatives together, then substitute the original x value back in for u, so the entire answer is in the correct variable. Let's lock in the blueprints. When you scan a complex equation, look for one of 3 structural patterns. If the functions are side by side, apply the product rule. If the functions are stacked as a fraction, reach for the quotient rule, following the required subtraction order in the numerator. If one function is trapped inside another, apply the chain rule, working from the outside in. Differentiation is a matter of architectural analysis. Identify the structure, select the corresponding rule, and execute the steps.